In mathematical optimization, the revised Simplex method is a variant of George Dantzig's Simplex method for linear programming. The revised Simplex method is mathematically equivalent to the standard Simplex method but differs in implementation. Instead of maintaining a tableau which explicitly represents the constraints adjusted to a set of basic variables, it maintains a representation of a basis of the matrix representing the constraints. The matrix-oriented approach allows for greater computational efficiency by enabling sparse matrix operations. Problem formulation. For the rest of the discussion, it is assumed that a linear programming problem has been converted into the following standard form, where A room times n. Without loss of generality, it is assumed that the constraint matrix A has full row rank and that the problem is feasible, i.e., there is at least one x0 such that x equals b. If A is rank deficient, either there are redundant constraints, or the problem is infeasible. Both situations can be handled by a resolve step. Algorithmic description. Optimality conditions for linear programming. The Karush-Kuhn-Tucker conditions are both necessary and sufficient for optimality. The KKT conditions of a linear programming problem in the standard form is where lambda and s are the Lagrange multipliers associated with the constraints x equals b and x0, respectively. The last condition, which is equivalent to 6 equals 0 for all 1 less than I less than n, is called the complementary slackness condition, by what is sometimes known as the fundamental theorem of linear programming. A vertex x of the feasible polytope can be identified by a basis B of A, chosen from the latter's columns. Since A has full rank, B is non-singular. Without loss of generality, assume that A equals Bn. Then x is given by where x b0. Partition C and S accordingly into to satisfy the complementary slackness condition. Let S be equals 0. It follows that which implies that if Sn 0 at this point, the KKT conditions are satisfied, and thus x is optimal. Pivot operation if the KKT conditions are violated. A pivot operation consisting of introducing a column of n into the basis at the expense of an existing column in B is performed. In the absence of degeneracy, a pivot operation always results in a strict decrease in CTX. Therefore, if the problem is bounded, the revised Simplex method must terminate at an optimal vertex after repeated pivot operations because there are only a finite number of vertices. Select an index m less than qn such that square less than 0 is the entering index. The corresponding column of AQ, will be moved into the basis, and XQ will be allowed to increase from 0. It can be shown that i.e., every unit increase in XQ will result in a decrease by minus square in CTX. Since XB must be correspondingly decreased by delta XB equals B minus 1 AQXQ subject to XB minus delta XB 0. Let D equals B minus 1 AQ. If D0, no matter how much XQ is increased, XB minus delta XB will stay non-negative. Hence, CTX can be arbitrarily decreased, and thus the problem is unbounded. Otherwise, select an index P equals oddmean 1 im xi, die greater than 0, as the leaving index. This choice effectively increases XQ from 0 until XP is reduced to 0 while maintaining feasibility. The pivot operation concludes with replacing up with AQ in the basis. Numerical example. Consider a linear program where let initially, which corresponds to a feasible vertex x equals 0,0,0,10,15 t. At this moment, choose q equals 3 as the entering index. Then d equals 1,3 t, which means a unit increase in x3 will result in x4 and x5 being decreased by 1 and 3, respectively. Therefore, x3 is increased to 5, at which point x5 is reduced to 0, and p equals 5 becomes the leaving index. After the pivot operation, correspondingly, a positive Sn indicates that x is now optimal. Practical issues. Degeneracy. Because the revised simplex method is mathematically equivalent to the simplex method, it also suffers from degeneracy, where a pivot operation does not result in a decrease in CTX, and a chain of pivot operations causes the basis to cycle. A perturbation or lexicographic strategy can be used to prevent cycling and guarantee termination. Basis representation. Two types of linear systems involving B are present in the revised simplex method. Instead of refactorizing B, usually and LU factorization is directly updated after each pivot operation, for which purpose there exist several strategies such as the Forrest-Tomlin and Bartels-Golub methods. However, the amount of data representing the updates as well as numerical errors builds up over time and makes periodic refactorization necessary.